Welcome to The Explainer. I'm absolutely thrilled to have you here today. We're going to dive right in and demystify something that you probably rely on, but let's be honest, almost certainly never think about. We are looking at the invisible lifelines that literally keep our railways running safely. Railway radio systems. So, I want you to think about this for a second. How exactly do massive, fast-moving metal tubes barreling at high speeds across vast and often super remote landscapes stay perfectly connected to control centers? It's honestly a massive engineering challenge. I mean, you obviously can't just plug a physical wire into a moving train, right? You have to rely entirely on the invisible, complex world of radio frequencies. Okay, let's dive into this. Here is our roadmap. 1. The Railway Radio Toolkit. 2. UHF and local station management. 3. GSM-R, the safety lifeline. 4. Public networks and passenger Wi-Fi. 5. The tunnel propagation problem. And finally, 6. Obsolescence and the future. Section 1. The Railway Radio Toolkit. So we're basically dealing with a 3-tiered cake of radio networks operating all at once. At the local level, we've got UHF handling station operations. Then, sitting right above that is GSMR, which serves as a dedicated, highly secure network for vital safety data. And finally, public radio, which comprises the commercial networks that provide stuff like passenger Wi-Fi. As you can see, each one has completely different functions and network architectures. Section 2. UHF, Local Station Management. Now, UHF radios, these are the real workhorses on the ground, but they operate on what's called a simplex system. Basically, that means you have to press a button to talk and then release it to listen. Since you literally can't talk and listen at the exact same time, this requires incredibly strict voice protocols and unique call signs. You absolutely need these rules to make sure there are no catastrophic misunderstandings on the tracks. These radios are mostly used for day-to-day stuff, station management, facilitating engineering work, and train shunting. Shunting, if you're not familiar, is just the process of sorting and linking train cars together. But here's what's truly fascinating. They use continuous confidence tones. Imagine a shunter standing right there on the tracks, guiding a heavy train backward by talking to the driver. The radio actually emits a continuous tone. If that tone stops, the driver immediately knows the connection is gone and hits the brakes. It's a brilliant, incredibly simple, fail-safe mechanism. Section 3. GSMR, the safety lifeline. Okay, let's talk about the mainline safety backbone. GSMR stands for Global System for Mobile Communications Railway. It's essentially a customized, locked-down, highly secure version of a 2G mobile network. But the massive difference here? Well, public networks optimize for revenue, right? So they accept a few dead zones here and there. But for a railway network, dead zones are strictly forbidden. It requires total, unbroken coverage along every single inch of the route on dedicated frequency bands. No exceptions. So the crucial point is what this network actually carries. It carries ETCS data, that's European Train Control System data, which allows trains to receive movement authorities directly into the cab, so they don't even have to look at line-side signals. It also uses smart addressing, meaning a driver can just hit a button and instantly connect to the signaler controlling their exact location. But without a doubt, the most vital thing it carries is the Railway Emergency Call, or REC. If a hazard is spotted on the line, hitting this button sends a high-priority tone to all trains within a specific cell area, bringing everything to a dead stop to mitigate an accident. And look at the operational equipment itself, like a signaler's terminal. It's explicitly engineered to prevent risks. For example, the system physically stops two drivers from talking over each other to the signaler at the same time because, well, that could mask critical safety information. Make no mistake, this gear operates in a much harsher, higher-stakes environment than your typical office phone. Section 4. Public networks in passenger Wi-Fi. You know, there is a somewhat amusing irony about modern railways. The absolutely vital safety systems that are out there preventing catastrophic collisions, they're largely running on super robust but undeniably older 2G-style architecture. Meanwhile, the passengers in the back are using massive modern 4G and LTE bandwidth to stream high-def videos and scroll social media, but actually getting that commercial bandwidth onto a moving train, it's notoriously difficult. 5 to 35 decibels. That is the massive amount of signal attenuation, or signal loss, caused by the physical body of a train carriage. I mean, think about it. Train cars are basically giant metal cages flying down the track, and they block radio frequencies exceptionally well. To put that into perspective, just a 3 decibel drop cuts the available power of a signal right in half. So a 35 decibel drop, that completely crushes external cell signals. 0 bars. So, How exactly do engineers fix this moving metal tube problem? They use DOBRs, or digital onboard repeaters. These are active devices inside the train that capture the weak external 4G or LTE signal, amplify it, and then re-radiate it through dedicated ceiling-mounted antennas right inside the carriages. And because that bandwidth is being shared by hundreds of people, operators often have to actively filter and restrict heavy video streaming or peer-to-peer file sharing just so everyone on board gets a reliable connection.
Section 5. The tunnel propagation problem.
Now we introduce a massive physical complication. Radio waves absolutely hate tunnels. Concrete, brick, and hundreds of feet of solid rock block invisible frequencies completely. And it gets worse. When a massive metal train enters the tunnel, it physically blocks up the space, drastically increasing the rate of signal attenuation. Check out this striking figure. If you stick a regular radio antenna at the end of a single-bore tunnel and transmit at 450 megahertz, the signal might only penetrate about 500 meters inside before it completely dies out. Poof, gone. Add a train into the mix or really tight clearances, and it's even worse. And don't even think about GPS. Satellite signals drop out completely the literal second you go underground. Now, what's really interesting here is the brilliant engineering workaround to this problem, the leaky feeder. Instead of trying to blast a signal from one end of a dark tunnel to the other, engineers string a special cable along the entire length of the ceiling. This cable actually has intentional slots cut right into its outer shielding. This causes it to intentionally leak radio frequencies evenly down the line. So regardless of passing trains, you get a solid, consistent signal all the way through.
Section 6. Obsolescence and the future.
We are rapidly approaching a looming technological crisis. The current GSM-R network relies heavily on aging technology. Crucially, early train control data uses what's called circuit-switched data. In plain English, that means a constant, dedicated connection has to stay wide open for the train's entire journey. So imagine dense areas like huge city stations. You've got thousands of trains all trying to hold open their own dedicated circuits, and it just completely clogs the network. The solution going forward is FRMCS, the Future Railway Mobile Communications System. This will shift everything over to modern packet switch networks like 5G, which are actually designed to handle massive amounts of data for both vital safety needs and our passenger Wi-Fi demands. Which leaves us with this final provocative thought to ponder. As we move rapidly toward a future of driverless, fully automated, and incredibly data-hungry railways, the physical tracks are going to matter just as much as the invisible radio waves in the air. The real question is, can our communication networks evolve fast enough to safely guide the trains of tomorrow? Thank you so much for joining me on this explainer today. Keep learning, keep questioning, and I'll see you next time.